Hi team. Yeah, hi team. I'm sorry for the delay. Okay, let us start. Team, before that, what I want to convey to the session is, this session goes especially on the fundamentals VLSI. Okay, yes, there will be few more sessions, maybe the 2 to 3 sessions coming to VLSI fundamental to cover all the VLSI fundamentals, including combinational, sequential, like in the design, like for example, synthesis. We say in synthesis, like we take check design to see whether the latches are there. In the design, unintentional latches must not be there. So what might be the reason? And even tri-step buffers also must not be there in this design. Why? For all these fundamentals, we must know the reasons. That's why team, this is only the first session, which will continue with the 2 more sessions to cover all the VLSI fundamentals related to PD. I'm not saying for others. Maybe this will be useful for them as well. But I'm strict to the point. For physical design, whatever the VLSI fundamentals are very much required. At length, we are going to discuss. Remember, this is not only the first and last session. There will be the continuation. Okay. Coming to VLSI fundamentals 1, team, here everybody says to technology word. People say, if someone asks me, which technology are you working on, which technology, latest technology, like that, people are entertaining. Fine. Before that, what is technology? How can you decide? And of course, there is a layman definition. I'm not criticizing anybody, but sure, there is a layman definition saying that the different, like the distance between the source and drain. Okay, that's right only. But you know, team, CMOS technology till, I mean to say, more than 28 nanometer technology only. So we follow CMOS technology till 28 nanometer. If you go below 28 nanometer, we are not considering the fit like CMOS. We went to FinFET. Hope you know. I'll show you the videos, images, and all. Sure.
Sir, your voice is breaking, sir.
I mean to say, below, is my voice breaking? Just a second. I'll come. Now, is it fine? Is it fine now? If not, please ping me. Okay.
Yes, sir. Yes, sir. It is fine.
Okay. Okay. Till 28 nanometer only CMOS technology. But from 28 nanometer to below, like say 3 nanometer, we consider FinFET. And if it is below 3 nanometer, we take GAAFET, GAAFET. It is gate all around FET. We will show you the diagrams and all. So team, remember, if someone asks you the technology and all, you must know the latest trends also. People say CMOS technology. No, that CMOS technology over. There is a FinFET technology. Again, we got some issues regarding mobility and all. Hence, we went to gate all around FET. Okay, let's start. See, we want to give just the definition of VLSI as it is VLSI fundamentals. In VLSI fundamentals, we want to integrate more and more components. That is a prime requirement. Yes, even functionality wise, speed wise, we think in a bigger picture. We want optimized values. We want as less as possible the size, the speed as high as possible, and even power consumption must be as less as possible. Even, you know, in our PD course, in our physical design, if someone asks me what are the goals of PD, what is your goal in physical design? The goal, you can say like PPA, like power, performance, area, or else ATP, area, time, power. These are the three goals. Of course, if something you want, you need to sacrifice. No pain, no gain. So here, the three parameters, you won't get all the three parameters in single plate. No, you can't get it. Suppose if you want timing, you need to sacrifice a little area or maybe power. If you want less area, then you need to sacrifice about the timing. But remember, trainees, among the three, the uh, the the prime requirement parameter is timing. Remember, even synthesis definition also the same. It is a process of converting RTL code to optimized gate level netlist by meeting the specifications area, timing, power, preferably timing. Timing is very important. Timing closure is very important. Remember. Now, coming to the PD goals, like it is a three parameters. Now, here team, coming to the MOSFET, let us start with MOSFET. You can ask me why BJT. BJT is a, just a second. BJT is a symmetrical device and it occupies more space. That is only the reason BJT is not preferable in IC fabrication. Whereas FET and MOSFETs are symmetrical devices. Symmetrical device in the sense both source and drain are equally doped. That means you can use the drain as source as drain. But whereas in BJT emitter is heavily doped, collector is mediumly doped. Hence, you cannot use the emitter as collector as emitter. So coming to the space, FET and MOSFET occupies very less space. Of course, FET has leakage current, hence we went to MOSFET. So coming to the MOSFET, just introduction, like regarding you can consider this. But is there any disadvantages in the MOSFET? It is like I can say each and every device in our about 28 nanometer technology, we follow CMOS technology. Whether it is a resistor, diode, capacitor, any device, we implement in terms of CMOS technology, PMOS and NMOS transistors. Yes. Why? What is the reason? See, in CMOS technology, like let us take a simple basic device, inverter, CMOS inverter. In CMOS inverter, for the static inputs, means input is logic 1 only, stable logic 1 or stable logic 0. In such case, uh, only one transistor, either it is a MOS, PMOS or NMOS. Team, one more thing I want to confirm. Whenever we, like the speakers or the third person is saying PMOS transistor, it is not really it is not a transistor, it is a MOSFET. So there we are using P, instead of P MOSFET, we are saying PMOS transistor or transistor. Remember, okay? I hope most of the people know, as the session is completely fundamentals. I'm thinking you don't know anything about the VLSI concepts, but team, please bear with us. Now, coming to the point, if you take stable input logic 1 or logic 0, in CMOS inverter, there is no connection from, suppose if you take logic 0, PMOS becomes on, but NMOS becomes off. So there is no connection from rail to rail, VDD to ground. If you take input as logic 1, then VDD, like I mean to say, PMOS will become 0, off, NMOS becomes on. Even in this case also, whether output is logic 1, logic 0, we are least bothered. Here we are bothered about static power dissipation. So coming to that area, even when the inputs are stable, in such case, there is no connection from rail to rail. Hence, the static power dissipation is almost negligible. I'm not saying 0, because whenever the device is on, there might be some leakage current. There will be, obviously. So I'm not saying static power dissipation is 0 completely, but there is a negligible static power dissipation. And remember, team, in our design, in our VLSI visual design, and other domains as well, whenever it is a power, it contains 3 components. One is static power dissipation, static power component. And even The dynamic power is contains like a switching power and short circuit power. Team, remember, in our case, whenever the input is, for example, it is if it is VDD by 2 specifically, but in general, if you discuss at a particular point, both PMOS and NMOS transistors, whenever the input is dynamic, I'm talking about dynamic input, 0 to 1 or 1 to 0. In that case, at a particular point, maybe in a fraction of microseconds, at a particular period of time, both PMOS and NMOS transistors becomes on. So they have some on resistance. In such case, there will be a huge current flowing through the, from VDD to ground. In such case, there will be a path that we call it as a low impedance path. So team, during that state, means during transitions, there will be a current in the circuit, there will be a power dissipation. That power dissipation is called like, you can take it as a switching power or short circuit power. In a, at length, you can say it is a dynamic power. So in CMOS, why the people at that time, they have considered CMOS technology. The reason is it has negligible static power. And of course, even if it is a PMOS family or NMOS family, there will be a resistor. Because of that resistor, there will be a heat. Even that heat also, like you can overcome, because whatever RL resistor, load resistor might be a passive load. Because of that, there will be a heat. Even that also removed in CMOS technology. Now, okay, this is a theory. Now, what happens when you come down to 28 nanometer technology, below 28 nanometer technology, we are not considering CMOS. Yeah, why? What is the reason? Here you can see team. Here, I have mentioned here at some instability. Even though like let us take CMOS. In CMOS, even we are lagging with electrostatic discharge, ESD effect. Whatever the SiO2 layer is very thin, and even if you're standing on the floor without any slippers, and if you touch the particular MOSFET through your finger, then MOSFET is going to do damage, because even our human has some potential which may disrupt, break down the SiO2 layer, through which the device is going to damage. So here there are some discomforts in the MOSFET or CMOS. That is the reason we are going for some other alternate, that is FET, what we call FinFET team. And you can see FinFET uh, team. Can you change the slide? Second one, yeah. So team, here you can see, okay, third one. Let me show some FinFET image. Not this. Stop the video. We will show it later. Now itself. Yeah, this one. Yeah. 1 second. Team, in CMOS or in MOSFET, we form the whatever the inversion layer, or we form the channel from the top only. So we create the channel from top only one side. Why don't you take in other sides as well? Like you can see the figure in this. See there, the red color one is the gate. Usually from the top only in one direction. But now in FinFET, you can see here from other directions as well, from left side, right side, and top, not bottom. Team, remember, not bottom. So we made the source and drain, the construction in such a way that the gate can form, like the gate covers the source and drain regions in all the three directions. I repeat, three directions. And this red color, it is just like a fish has fins. So we call them as the FinFET. Here, the gate, whatever. Here, you can see that in a fit, like in a fin's shape. Hence, it is a like fin. And team, remember, like we will show you one video to give you the pictorial or visual representation about FinFET. And remember, if you go beyond below 3 nanometer, we are not at all considering the FinFET because of some issues like mobility and some issues. Hence, we go with the gate all around FET. Now we will show you the visual representation of FinFET. Okay, please watch the video clearly. And once sure, if PPT also, the concerned team will get back to you regarding the video and all. Okay, now can you play the second slide video? The video it is yeah, this one. Play, please play the video. Can you play one more time? Yeah, can you play the video once again? This is MOSFET. Now the gate is covering in all the 3 directions. So efficiently you can form the channel and you can generate the current. Yeah, that's it. So it's faster, smaller, and lower power team. Fine. This is what I want to take the stand about FinFET. And next slide. Next slide. What next slide? So team till 5 nanometer. Yes, it is FinFET worked out, but because of scaling down, yes, we faced some undesirable some effects in terms of variability, mobility and all. That's the reason again we moved to gate all around FET. Next slide. That is GAAFET. Yeah, here in gate all around FET, we form the gate layer is covering the source and drain in all the 4 directions. In FinFET, only 3 directions, but now it is all the 4 directions. Next slide. Next slide. Yeah, you can see here now. See here, the blue color ones are source and drain. There you can see from top, left and right, not bottom. But whereas in ribbon FET, which is a GAAFET, you can see that even from bottom side also, the gate is covered, the whatever the layer. Hence, team in GAAFET, it is happening in all the 4 directions. So efficiently you can form the channel, or else you can make use of it. That's what. Okay, this is what I want to conclude regarding the technology team. Okay, so it's 28 nanometers CMOS, and then it is FinFET, and then it is gate all around the FET, GAAFET. Like these are very important during your course and during even in interviews as well. I want to conclude that regarding the technology word, only word. That's it. Now, next one. Yeah, this is just it is like a conclusion. Next. Yeah, stop. So team Here, whatever is happening, the industry has two sides. One is front end, another one back end. We, the people, from synthesis onwards, it becomes back end. Before synthesis, everything is front end. So whatever the people idea, it's just like a counter or D flip flop or something else, your own idea. First, that idea is a thought. That is only the catalyst to our design. So that thought becomes, yeah, anything? Can I continue? Okay. So team in front end, whatever the thought uh, might become as a program, sorry, code, RTL code. It is register transfer level code. That remember that code, whatever you have written, that you are going to write, you are making finalization, that is independent of the code. Independent of the technology, sorry. But whereas from synthesis, even in synthesis, in synthesis, there are three steps, right? Syn generic, syn optimization, and syn mapping. In the third step in syn mapping stage, there the technology related files like the technology mapping happens. Before that, it is independent of technology only. I want to make it clarity. And remember team, whenever you go for lower technologies, remember uh, the frequency of operation will increase. So people are going for lower technology nodes, 3 nanometer. No, people are going for 1 nanometer. Samsung is already reached, but the people are discussing. If you are going for below nodes, remember they are going for high frequency of operation. Yes, that is only the reason like they are going for higher, like lower technology. It doesn't mean that for every design you need to go with lower technology. No, see, for that application, timing. For your application, there might be some other constraint. It is not like always you need to work with lower technology nodes only. No. It is related to, it is depends on design. Finally, design only decides whether which fabrication house, which technology under. Okay. And team, remember, whenever you go for lower technologies, the yield means the positive outcome, the output, whatever when you separate the defective devices, the good devices, good out of total is simply I can say yield. That yield becomes less because of that high frequency. Okay, even the cost as well, it increases. Now, team, as I said, in CMOS, no need to worry about static power dissipation. We need to worry about power, dynamic component, power component only. And that is team as a like just just as a bird view, square F, where that F is a like a frequency of operation, and it's a power supply ADD, and it's a capacitance. Yes, of course, there is a switching factor alpha as well, but just I'm giving you the definition because as we are the VLSI fundamentals, I'm not I don't want to create disturbances in the flow. Okay, sure, I'll take the alpha, whatever that also, but not now. Now, team here, we people think if we reduce the voltage of operation, then dynamic power may reduce now. Yeah, that is true. Accept. But team, we know that noise margin. What is noise margin? It is the ability of the device, particular device, even though noise is included, whether whether it is influencing the output or not, whether logic 1 becomes logic 0 because of this noise, or logic 0 becomes logic 1. It doesn't happen. If it is not happen, then it has a good noise margin. So I can say related to the noise, is it resistive to noise or not, that output. So when you come down, yes, there is an advantage. Participation reduces, but noise margin also reduces T. You know, if a device is resistive to the noise for a 1 volt noise, then good. If it is a 2 volts noise, then also it is super because 2 volts noise is occurred. Then also our design is not at all sensitive to that 2 volts. We are working on it. Our output has not changed. You can say in that way. So in general, not in general, specifically noise margin must be maximum. So even in CMOS also, that is maximum T when compared with PMOS and NMOS. That is also one added advantage in CMOS. So here when you go for lower voltages, then the noise margin reduces, which is a disadvantage. Hence, in every design, reducing the voltage is not the permanent solution regarding the dynamic power. Okay, that is also one of the point team. And now team, as we are strict to our point physical design, what we think, are we interacting with the D flip flop or PMOS or NMOS or logic gates and all? No. Remember team, in our backend, there are different domains like analog profile, physical design, static timing analysis, STA, or even if the entire IC is designed, then also there will be a post silicon validation. If the IC is ready, they'll check whether the IC is functioning properly or not. Those are called post silicon validation engineering at that section. Okay. Now I'm considering the physical design. Remember team, in physical design, we start our journey with standard cells. Remember, we people say in digital, the basic device is logic gate, AND gate, OR gate. If you take half adder or carry look ahead adder or anything, you will get gates only like that. Yes, that is true. But when it comes to the physical design, remember again and again, we deal with standard cells. Remember, beyond the standard cells, it could be a macro, it could be a memory, it could be a PLL. We think that is a standard cell, a bigger standard cell, like that. So I mean to say, the even here you can see the design team. Here, the base layer contains all the PMOS, NMOS, and semiconductor related materials, and M1 layer contains whatever the devices metal pins, and from metal to from that onwards above, you will use it for interconnections. So here it is like a apartment culture. In ground floor or in cellar, the devices might be there. The connections comes from first floor, second floor, third floor, again second floor, first floor, and again to the cellar. The connections goes in this way. Here it is a simple figure showing that the blue color contains all the PMOS, NMOS related devices, and the connections from there like metal pins and then connections like that. Now, my point of interest is in this session, uh, how I can give the connections. It is, we call it as technically routing. It is not routing, students. Team, remember, it is not routing. Please don't pronounce it like routing. It is routing. How can you give the routing? It is like horizontal, vertical team. If you want to go for from first layer to the another layer, like second layer, third layer, whatever. Remember, metal layer 1 will be horizontal, then metal layer 2 will be vertical. Metal layer 3 will be horizontal. Metal layer 3, 4 will be vertical. Like it is a horizontal, vertical type. Here you want to know why it is horizontal, vertical. Why don't you take it in a normal way, like all our basic electronics or devices components, how you connect with the wires? Why don't you go like that? No, we are not going. What is the reason? That if you want to know the reason, you must know about the capacitances present in the device. Basically, there are 3 types of capacitances in the design. Okay, next slide. Yes, team. Here you can see, keep these various capacitances. Team, remember, as I said, in our physical design, timing is very important. The timing is affected by resistance and capacitance. So it is like whatever the coming to the metal layer resistance, yeah, you can consider the resistance, but the capacitance is very important because there are three capacitances because of that, like that metal. Coming to the metal are two metals. Those three capacitances are area capacitance, fringing capacitance, and coupling capacitance. If you take a metal layer, for example, here you can see a rectangular metal is there. It has some length, width, thickness T. But you see from the ground to that particular layer, whatever the height, that height also matters. So remember team, if there is a metal layer 1, there is a metal layer 3, because metal layer 3 will be uh, more far away from the ground. So remember team, higher metal layer, which is metal layer 3, has less area capacitance. Capacitance is very, very important. And team here, I want to make sure that one point saying that why don't you consider inductance? Because any device, whatever it has, uh, uh, what I can say, like, just a second, team, just a second. Yeah. Why don't you consider inductance? Why only resistance and capacitance? Team, remember, whenever the metal wire or anything, if the size is in terms of beyond millimeters or in terms of around micrometers, then in such case, I mean to say in millimeter size, in such case, inductive effects happens. But when you go below micrometers, then in such case, inductive effects might not be there. Sure. That is only the reason everywhere we consider resistance and capacitance only, not inductance. Because the size is very, very less. I mean, less than nanometers around we are present. So in such case, in such a example, you don't get any inductance, remember. Okay. Now here there is an area capacitance. What you need to know is if the metal layer or net, if it is going above, then its area capacitance reduces. According to this formula, as H increases, area capacitance decreases. And there is a fringe capacitance also team, because whatever that below that layer, the side walls, because of that, there will be a capacitance that is a fringing capacitance. So in that various capacitance, area capacitance and fringing capacitance. And the last one team, next slide. Next slide. Yeah, coupling capacitance. You see here team, that is epsilon L dash T by D. What is L dash? That's overlap length. If two metal layers having the length, overlapping length L dash, if there is a more overlapping length, then your coupling capacitance will increase. Yes, that is the reason. Here, what we do is, we take each and every metal layer, like metal layer 1, metal layer 2, in a horizontal vertical way, so that the overlap length reduces. Of course, that metal and metal, there is a distance T. It also depends. But here the point is, why we are going for horizontal, vertical type of routing. The reason is overlap length reduces. If overlap length reduces, coupling capacitance reduces. If coupling capacitance reduces, the net delay reduces. If the net delay reduces, timing closure becomes easy. So team, in a single word, what I want to convey, the routing is horizontal, vertical only. The reason is so that overlap length reduces, coupling capacitance reduces, hence delay at that whatever the value reduces to. That's what the point. And you can ask me how the delay is interrelated with the capacitance. Yes, team, each and every tool vendor follow their own strategy. They don't reveal to the public domain. This is the strategy that we are following. No, they don't reveal it as per their security guidelines. But what I want to convey to you is, if there is a metal wire or net, how can you calculate the delay for that? Means there is a standard procedure called Elmore delay. Okay. Uh, you can go to the last session. Yeah, here Elmore delay is there. See team, here tau is equals to 1 by 2 RCL square. Means the net delay tau is quadratic function of length, net length. Suppose if your net length is a bigger one, is a larger one, then will be a more delay. If you reduce the net length half, for example, then the net delay reduces by 1 by 4 times. So there is an enormous reduction in the net delay when you reduce the net length. This point you must know, because now afterwards we are going to discuss about delay optimization techniques, insertion of buffers. How come insertion of buffer is reducing the delay? When you insert the buffer, the net length reduces. There are actually two net buffers only. Now in the middle, you have placed one more buffer so that now the length becomes half L by 2. So according to this Elmore delay concept, the net delay even reduced to 1 by 4 times. So team, remember, the net delay is directly proportional to, directly proportional to the square of the length. So be careful. You need to have the net length as small as possible so that you can fix the timing in a good way. That's what I want to say.
Hello, sir.
Even I want to show you how it is horizontal vertical connections are happening. Previous slide, please.
Hello, sir.
Yeah, yeah,
Sir, this is L2 or L square. You are saying quadratically that I didn't get.
yeah. That is L square only.
Okay, okay. You are saying L2. That's why I thought what is
Yeah.
L2?
Okay. Actually, in PPT, I was unable to make it as L square. I thought of taking some caps and all, but anyway, yes, you are right. It is 1 by 2 RC L square. The net delay is a quadratic function of length L square. Tau is directly proportional to L square. Okay. Yeah. Yes, team, you can see here metal layer 1, metal layer 2, the directions and all. See, there is a metal layer 1 right side figure, the horizontal. Now, there is a metal layer 2, M2, that will be vertical, remember. And again, M3, horizontal. M4, vertical. So remember, if M1, like M1 is horizontal only, then M2 becomes vertical. In that way, horizontal, vertical, horizontal, vertical. Suppose you want to make a connection between M4 to M1, then what you do? We put a via. It is not via T, it's a via, VIA. So by placing vias between metal layer 1 to metal layer 2 and then metal layer 3 and then metal layer 4, you can make the contacts or connection between metal layer 4 and metal layer 1T. Okay, there are different vias called double cut vias, all these things we will see like whenever it whenever it requires and whenever it is in our flow. Where because team, please trust me, we have a clear roadmap. Okay, in this VLSI fundamentals, from each and every word, we will give you in a particular way, like how you must be a good PD engineer, what might be the basics and that. Okay, please trust us. Sure, we will take each and every point, whatever you raised or whatever you concern. Sure. Okay, coming to the routing type, just I am giving you here. It is horizontal, vertical, so that coupling capacitance reduces. That's it. Okay. That's what team. Actually, I'm very sorry. I made you to wait for more than 15 minutes. I'm very sorry, team. Next time, sure, I don't repeat this, and we will continue the remaining the VLSI fundamentals in upcoming sessions. Okay, and if you have any queries, you can type in the chat box. Now I'm checking the type in the chat box. Okay, and even
Hello, sir.
yes.
Sir, can I ask a query, sir?
Yeah.
Hello.
Yeah, you can ask.
Sir, okay, sir. Sir, so like you said, na, more than 28 nanometer, we used CMOS less than 28 nanometer to 3 nanometer FinFET. So can you repeat that, sir? Means what was the advantage of using, why we were using CMOS and why we left CMOS after 28 nanometers and then to FinFET? That I didn't get clear. Hello, sir. Am I audible? Hello. Hello, sir. Sir, your voice is not coming.
Yeah. Sir, your voice is not coming.
Okay, team. If you have any doubts, you please get back to our team. Okay. They'll share the questions. Sir, FinFET
Hello, sir.
also consists of PMOS and yeah, yes. See, the FinFET contains uh, different construction. In MOSFET, it is the whatever the layer is implanting on what is the PMOS NMOS. The construction, you take one MOSFET, one FinFET, both the figures, and you compare. The construction is different. Okay, team. Can we?
Hello, sir. Hello, sir.
Can you please? Can you
Sir, I
repeat
had
why
a
we
doubt, sir.
don't? Yeah, what is the
Hello.
doubt?
Sir, I asked already, sir. Means that means what was the reason why we left the CMOS after 28 nanometers and why we start using FinFET and get all around that I that I have confusion is why we started using that. Can you repeat it again, sir?
That's yeah. That's what. See, if you take CMOS, I mean CMOS technology, that whatever the channel length. See, the source and drain, the distance between the source and drain is only the channel. Like the technology node, whatever. When you are moving down and there will be some other issues, like especially in CMOS, you take some electrostatic discharge effect, ESD effect, or even you take the formation of the inversion layer, the channel between the source and drain. In MOSFET, it is happening only in one direction, right? But in FinFET, you can form the inversion layer so that effectively gate can control in three ways, right? That is one of the reason. Okay, team, I'm getting late. Can we have this doubt session in upcoming session? Okay.
Okay, sir. Okay.
Guys, sir, have the meeting actually. So we will take that out in the next class. Sir, have the urgent meeting.
Okay, sir. No problem, sir.
Thank you so
Thank
much.
Yeah. Thank you, team. Thank you for your support. Thank you.
Thank you so much. Thank
And
you so much, guys.
we'll meet on another session. Yeah.
Yeah.
Jai Hind, team.
Jai Hind. So.
you. Jai Hind.